Today's class, let us see about matrices. Matrix has a wide role in the field of engineering. So it has many applications in many branches of applied mathematics, such as algebraic and differential equation, theory of electrical circuits, etc. So let us see how to find the characteristic equation. So to find the characteristic equation, consider the linear transformation y is equal to ax. So in general, this transformation transforms a column vector x is equal to x1, x2, etc. xn into another column vector y is equal to y1, y2, etc. yn by means of the square matrix A. So actually, we are using the column vector x to transform column vector x into another column vector y. So for this we use the transformation y is equal to a into capital X. So the square matrix by means of a square matrix capital A. So what about capital A? Capital A is the square matrix. So the order of the matrix A is m by n. So it has m rows and n columns. The elements are capital A is equal to aij. That is A11, A12, etc. A1n, and the last row is AN1, AN2, etc. ANN. So already we know that the linear combination of vectors. A vector capital X is a linear combination of vectors x1, x2, etc. xm if x can be expressed in the form x is equal to lambda 1 x1 plus lambda 2 x2 plus etc. lambda m xm. So in this case, if all the m vectors are linearly dependent, then at least one of them may be expressed as a linear combination of the other. And the rows and columns of a given matrix will be linearly dependent if the determinant value of a given matrix is 0. The rows and columns of a given matrix will be linearly independent if the determinant value of a given matrix is not equal to 0. Okay, so we have seen the matrix A, and if a vector capital X, if it is transformed into a scalar multiple of the same vector, and y is equal to lambda x, and that is equal to A into capital X. So therefore, on multiplying that lambda x with the unit matrix, which is of order n, so we will be getting Ax is equal to lambda I into x. So therefore we will be getting Ax minus lambda I into x is equal to 0. That is A minus lambda I on x equal to 0. So which is nothing but the characteristic equation. So the equation determinant A minus lambda I equal to 0 is said to be the characteristic equation of the transformation. So determinant A minus lambda I is equal to 0. So we will be getting the equation according to the order of the matrix. If the order of the matrix is 3, then we will be getting a cubical equation. If the order of the matrix is 2, then we will be getting the quadratic equation. Now solving the determinant A minus lambda is equal to 0, we get n roots for lambda. So all these n roots, we call it as a characteristic roots or eigenvalues or latent values of the matrix A. Okay. So the determinant A minus lambda is equal to 0 is nothing but the characteristic equation of the transformation. So solving determinant A minus lambda is equal to 0, we get the eigen roots. So after getting the eigenroots, we will be finding the eigenvectors. So how to find the eigenvectors? So corresponding to each value of lambda, the equation, going back to the equation Ax equal to lambda x, and that has a non-zero solution, vector x. So solving, we get the latent values of the matrix A. Then we are going to find the eigenvector. So corresponding to each value of lambda, the equation Ax equal to lambda x has a non-zero solution, vector x. Now let XR be non-zero vector satisfying Ax equal to lambda x. So here we are going to replace the lambda by the eigenroots. So based on the degree of the roots, we will be getting degree of the equation, we will be getting the number of roots. Suppose if n is equal to 3, we will be getting 3 roots, and therefore we will be replacing lambda by 3 roots. So the first case we will be replacing lambda by lambda 1. Second case will be replacing lambda by lambda 2, and so on. So here I have taken in general when lambda is equal to lambda r. XR is said to be the latent vector or eigenvector of a matrix A corresponding to lambda r. Okay, so in the next class we will be seeing about the characteristic polynomial. So finding the determinant A minus lambda I, which can be expanded, and that will give a polynomial which is called a characteristic polynomial of a matrix A.